Okay, so thanks for the nice introduction. Well, as you have already heard, I'm Jonas Berges, and I'm gonna tell you today something about our resist materials, what can you use to pattern into, and the tip lifetime. How long can you pattern with the machine? So we'll have split this in these two topics. We start off with the resists, what we need for properties, as what makes polyphthalaldehyde so special and what else can you use. Then we go on to this tip lifetime and have a closer look what happens at the tip and the endurance, how long can you write with the tip. And in the end, we have a short outlook about current research and where we are going now with the resist systems and tips. So we start off again with this nice video that most of you probably already have seen of the function scheme of the NanoFrazor, where we write with a hot tip into our resist and we read back with the cold tip the written pattern. And we have this grayscale image as input that corresponds to the depth levels that we pattern, and with the cold tip we create an AFM image. We will focus now what's going on with this blue stuff here, the resist. What does it take to write into a resist with a hot tip, and what properties are important, and how can we modify it, and what else happens? The second part is a close look at this interface. What happens exactly at the contact point between the tip and the resist? Do we have build-up and wear on the tip? This contamination, it will be a bit closer defined. And how long can you write with a tip until you have to exchange it again? So let's start off with the resists. We have a huge list of properties that we want to have to consider for thermal probe lithography. Basically, we start off with the mode of removal. How do we remove the material? What happens with the material after removal? Then certainly there is the thermal properties to consider for thermal probe lithography. Then the decomposition. How does this material decompose? What happens to it? And everything around the patterning is also really important. The handling, the processing, how do we get the resist on top of our sample with spin coating or PVD or any other coating. Then there is also the etching to consider, basically the post-processing. After we've patterned with the NanoFrazor, we still need to do the pattern transfer into our substrate or other transfers with lift-off processes and anything. And certainly, as always important with chemicals and substances, are the stability, shelf lifetime, toxicity. Everything around this is also an important factor to consider when choosing a resist system. We'll start off with the resist removal. In our recent review paper on the overview of thermal probe lithography, we had this nice graph that shows the two ways of removal of material with a hot tip. One of the basic ones is the indentation. There we actually don't even need a hot tip. We push in with the tip and create the hole and push the material aside. But this, however, has some issues, as the material that gets pushed aside is still aside the pattern. So we can create a pileup, and this limits our choice of geometries. If we have a pixel that we've written previously here, then this pileup can basically backfill the pixel up that we wrote and change it after it's been written. Another issue that we have to consider is the melting and thermal properties. If you have a low glass transition point, basically a glass transition that happens before the decomposition, you can get a liquid state and start to smear the polymer across the surface, as we can see in this pattern where we wrote from left to right. And we can see there is this liquid things of polymer that get smeared across the surface. Therefore, in our opinion, the best thing that we can do is sublimation. We indent with the hot tip, and everything that gets in contact with the hot tip gets directly changed into the gas phase. So we don't have any residues as it's completely removed. We don't have any pileup on the sides of the pattern, and we get a nice clean indentation or hole where the tip has indented and no more material around it. Then in the decomposition, we have two effects that at the first look might seem like the opposites of each other, the self-amplification and the self-limitation. They are, however, not the opposing effects, but they are two different things that can happen both in a single resist. The self-amplification means that we can unzip a whole polymer chain upon a single heat trigger. In this example, if we break with the heat trigger here this carbon-oxygen bond and the polymer is self-amplifying, then this unzipping reaction spreads across the whole polymer chain, so like around this, and we're left with 5 volatile monomers. If a polymer is not self-amplifying and we break this bond, then we here in this example we're left with a polymer chain, and we have to break this bond again, and this bond, and this bond, and this bond to get to the same 5 volatile monomers. This can, if polymer is not self-amplifying, then this can lead to an incomplete decomposition, and we are left with residues. The self-limitation basically is the heat output of the reaction. If you have an endothermic reaction of this breaking of the bonds, then there is no further heat source induced to the system, and the whole unzipping reaction is very localized to the tip, heat influx zone of the tip. If we have an exothermic example and we start to pattern at different temperatures, like in this example of King, they used a polymer that is exothermic. Then if you pattern at a lower increased temperature, the lines get a bit wider because you input more heat. And at this point, what we think happens is basically a small runaway reaction, that each of this breaking of the bonds created a new heat source that started to spread more heat and triggered more chain breaking events, and basically got a very wide patterning and running. Basically a small runaway reaction that created a big pattern that's also quite unwanted. So what we would like in a resist is a self-amplification and a self-limitation by being endothermic. And such a resist actually exists. That's the polyphthalaldehyde that we also recommend to use for the NanoFrazor. It is self-amplifying across this carbon-oxygen bond backbone of the polymer chain, and the whole unzipping reaction is endothermic. We can use a wide temperature window for patterning from 500 to 1300 degrees heater temperature. The decomposition temperature of this PPA is about 180 degrees Celsius, and the glass transition temperature is above the decomposition, so we don't get any liquid state. So some of you might ask, well, if decomposition temperature is 180 degrees and we use a temperature window of 500 plus degrees, what does this mean? So here we review the heat transfer in the tip shortly again, as this heater temperature that I mentioned sits actually on top of the tip, and the decomposition temperature is measured at this interface temperature between the tip and the resist. So we lose a lot of temperature by the heat transfer from the heater to the tip. Therefore, we need to set a much higher temperature than the actual decomposition temperature. The upper temperature limit is basically another phase change that we have to consider, and this is the melting point of the heater. At about 1400 degrees, silicon will melt, and we will basically destroy our heater if we increase the temperature even more. But this gives us quite a nice temperature window to play with. And in the end, this temperature means how much heat do we put into the sample. The higher we go with the temperature, the more heat flow we get into the substrate, and we can control quite nicely how much volume we remove with a single indentation. The other mentioned properties like the handling and stability are also quite good of PPA. We were able to store solutions for over 3 months at room temperature and still pattern quite nicely on them. we still recommend to store solutions and powder in the freezer, and we have a shelf lifetime of way over a year in the freezer of the powder. We have a quite good dry edge processing window for further post-processing. It's easy to spin coat the sample in a variety of thickness from 2 nanometers up to 10 micrometers. And there has also been a lot of research done on this PPA. We had a big Eurostars project from 2014 on with 5 partners where we analyzed this PPA and improved the quality quite a lot. So we got a longer endurance to write and got a further understanding what is important. And also from this Eurostars project, one result is that the polymer is commercially available from Allresist, one of our partners. So you don't have to mix it up yourself, or you can simply order it, put in a solution and use it. There's also a lot of processing knowledge available from our team here of the applications. So if you have any questions how to go on with the patterning, just ask them and they will be glad to help you. So what else is out there other than the PPA that has all these nice points? We have seen a lot of resists that have been tested, like PMMA copolymer, that's also commercially available, but it shows a bit of increased contamination compared to polyphthalaldehyde. But nonetheless, Nolan Lessalin, who also had a recent webinar, had a quite good success with this resist and was able to pattern his Fourier surfaces quite well, from what I've heard. Then there are other resists like Caesar. It's also commercially available from Allresist, that can be used for special application where you need to use different solvents, but it also shows increased contamination. There have been tests with molecular glasses that are smaller molecules and therefore would allow for lower line edge roughness. They can be coated with from the gas phase for a very conformal coating with PVD, but they show a different issue. They show some redeposition and reflow. So here in this example where they patterned this nice mountain pattern, it can happen that these molecular glasses are not stable over time. So you might pattern them, but if you read this image again, it can be that the material starts to reflow and basically fill back up this pattern and is not stable over time. There have been polypropylene carbonates that also show increased contamination and also have a low glass transition temperature where we have this melting issue and smearing. Then there's polyolefin sulfones that are quite promising, still in an R&D stage, but they also show another issue, that's the lower dry edge resistance that limits your further processing. This might sound quite bad, but in the end, all of these resists have been used for patterning. They were able to successfully pattern in them with hot tips. So they all have their points to use and can be tested out if you have a special application that requires a different resist. To sum it up, PPA shows the best performance and it's a lot of knowledge available and you don't have to do a lot of work yourself. You can get this knowledge from us if you want something. And there are some upcoming or repeated webinars on the whole processing, etching, and pattern transfer from my colleagues Emine and Tero. You can use a lot of other resists as we've tested with many different partners. They usually show some drawbacks like increased contamination or the stability over time and a bit lower edge resistance. But it's really easy to try out new resist systems in the NanoFrazor. You don't have to consider contaminating your system. You put in a sample and test it, see if it works. Quite fast done. Now I talked a lot about this contamination, and in the second part of this webinar, we will have a closer look at the tip lifetime, this tip contamination, what happens at this interface. So at the tip, we have basically two opposing effects. We have tip wear and tip contamination. The tip wear happens when we move the tip across the surface and it gets worn down. Basically, instead of this nice sharp tip, we get a blunter tip that limits our resolution because the tip diameter is bigger. This usually is not such a big issue for us because the tip is never in, or rarely ever in contact with the hard surface of the substrate. It usually is only in contact with the soft resist material, and tip wear doesn't happen that much. The main issue that we know of is the tip contamination. This limits our resolution as we start to grow something on the tip, but this also increases the tip diameter. And it also limits our heat flux, as this contamination often seems to be insulating and we get worse heat transfer. Here we have an example where we did some SEM images of a tip in a quite fresh state. Then we did a lot of patterning, took it out, did an SEM image again, and observed these changes over time. We start with the fresh tip, then there's something growing, 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 and even more growing. And this is one of the main challenges that we face with these tip and resist systems. This heat transfer has been covered a bit in more detail by my colleague Anja, and these past webinars will be online soon, I think, for all those that have missed them or want to look at them again. So can we only observe this tip contamination in a TEM or SEM? Actually, we have some tools inside our tool to estimate this tip state and tip contamination in the NanoFrazor itself. For one thing, we can approximate the tip geometry by doing the approach curves. Before each pattern, we bring the cantilever slowly into contact with the surface to measure the distances and everything. And during this, we record an approach curve like this. And this tells us a lot about the adhesion length. Basically this triangle. And the larger this gets, this tells us we have a larger tip adhesion to the surface, and this usually corresponds to the tip diameter. So if this triangle here gets larger and larger, we see that we have a larger tip diameter. We can also get basically the tip height, this distance, from this approach curve, and therefore have two nice parameters that tell us a lot about the tip state already. The second part is small changes at the tip when there is something smaller than this growing also change the patterning performance a little bit. But this will be usually just compensated by the feedback as we do the patterning and then we read, and the software evaluates how close we were to the pattern and corrects small errors quite nicely. And we don't really have to worry about small changes as they will be compensated. There has also been a talk about this closed loop lithography, the feedback systems by Fabian, and this I think will also be online soon to rewatch if you missed it or want to see it again. So now the big question is, where does this contamination or dirt, as we can call it, comes from? From what we know, the resist is the main source of the contamination. And in this Eurostars project, we've seen that the purity of the resist is from the utmost importance. And the more pure the resist is, the less contamination we get. The environment itself is actually not such a big factor. We can pattern in ambient air. We actually wouldn't even need a clean room or inert gas, as we can actually run the NanoFrazor quite nicely in an office building. Also, particles on the surface are not nice, but usually don't affect the patterning that much. Here we have an example where we've seen some particles on the surface, but as you've seen, everything around the particle looks just fine. So the feedback had no trouble to work around these particles and fix these small changes. There is the possibility to use inert gas. You can flood the larger system, the Explorer, with gas, or you can put the smaller system, the Scholar, completely in a glove box if you need inert gas, like if your substrate requires this. But the resist or the patterning itself does not require an inert gas or. So then some of you might ask, if you have the initial state and we have this contamination, this looks quite fragile. Can we go back by cleaning the tip somehow? And indeed, we had some good success with some experimental procedures to clean the tip. One thing is basically turn on the heater in air, raise the tip temperature to a couple of 100 degrees, and hope that this contamination will simply evaporate. The other thing is what we call a tip scratch. And it's actually quite somewhat funny that we deliberately crash the tip into the surface, usually a hard surface like the silicon, to apply a mechanical stress and break off some asperities. This usually works quite nicely, but it's a bit of you need a bit of luck, but it can work. Then there is also plasma treatment you can use to burn off organic particles. Then now we come to the big question. How long can you write with such a tip? When I had my first interview almost a year ago, I had the lab visit and I was asking the same question. How long does such a tip last? And usually this answer is, well, it depends. And indeed, the answer is not that straightforward. It depends on what pattern you pattern, what temperature you set, what your read forces are, what your write forces are, the read-write ratio. But from our standardized test that we started to perform with quite large patterns, and our criteria was that the patterning error is less than 3 nanometer RMS. By improving this resist purity in this Eurostars project and even further, we were actually able to improve this patterning performance by quite a lot. We started off with, in 2013, with like 1 cubic micrometer of removed material until the tip had to be thrown out. And now we're at over 5,000 cubic microns. So this is quite an improvement over the year. And you see the curve goes up, and we hope to improve this value even more. But for most of you, probably 5,000 cubic microns, it's not really a number that you can relate to easily. Here we have some comparison to the tip size. So a small tip size is tiny compared to even a single cubic micrometer. And if you go to 5,000 cubic micrometer, we have a nice image that of this ton of this 5,000 cubic microns, only a tiny fraction actually stays on the tip and starts to contaminate. And 5,000 cubic micron corresponds to about 2.5 billion of these indents, basically pixels written at 10 nanometer depth, or 1 square millimeter of written area at 10 nanometer depth. So that's quite a lot for such a small tip. And we are still improving, as you've seen in the previous graph. So what's going on in our lab and current research? How do we want to improve the systems even more? As I've mentioned now a lot of times already, the PPA is already a really good resist, but there's always room for improvement. For one thing, we would like to improve the edge resistance and improve the laser performance with our laser writer, and reduce contamination, improve tip lifetime even more. So let's have a closer look. To increase the edge resistance, we have chosen a silicon-enriched PPA with one of our partners from Allresist, and could actually found out that the edge resistance is about 2 to 3 times higher in the reactive ion etching. Therefore, we can use thinner films, and with thinner films, we can get higher resolution application, pattern transfers, as you see some examples of the current testing that we're doing. The silicon-enriched PPA has a small side chain of a silyl side group on this PPA. The laser writer is quite a new product, and I think my colleague Simon talked about this recently. We had one of the current issues with the laser writer is that the PPA doesn't absorb a lot of this laser power. It's quite transparent. And we get some interference effects in the film itself. And therefore, we also have the problem that it depends on the laser absorption, depends on the thickness of the film. So if you have a resist thickness of 120 nanometer, we get a low absorbance. If you have one of 100 of just 60 nanometer or 180 nanometer, we get a high absorption. And this is a bit tricky, as we always have to simulate the sample or fine-tune the laser parameters, and we would like to be independent of the resist thickness. One of the goals that we are working on with two partners is to add a photoacid generator, basically a small molecule that upon the exposure to light breaks down into an acid. And then we get instead of a heat triggered decomposition, we get an acid catalyzed decomposition of the PPA. And we're not just limited to the laser power, we just can also use the light itself as a trigger for the decomposition. This also gives us the potential for faster laser writing. But it's still a long way to go, as we see this image. With the laser, I just wanted to pattern this tiny little arrow, but a little bit of scattered laser light was enough to trigger the photoacid generator and get a large decomposition on the sample ready. And by accident, we created a photomask with our own cantilever. So this happens, and we have to fine-tune the concentration of the photoacid generator even more. And one really interesting project that we're doing with the Cole group from Georgia Tech is to use a PPA copolymer with an aliphatic aldehyde, like in this example. And this promises us a lower decomposition temperature compared to pure PPA. So in this example, we did thermogravimetric analysis, and instead of 180 for the pure PPA, we got 120 decomposition temperature. We hope that we can actually increase the endurance of the patterning compared to the PPA. And so far in the first test, it's at least similar endurance to pure PPA. But in this small graph here, we see that at the same settings, 800 degrees, 6.3 volts of force, we were actually patterning like 40 nanometers deep in PPA, but almost 70 or 60 to 70 nanometers deep in the copolymer. So it decomposes much easier than the normal PPA. Then there's always tip improvements going on, like we have new cantilever design that we hope improves the patterning performance, and we would like to actually also understand the science between the PPA decomposition and tip contamination even more. So we have some TM images where we also do EDX mapping to check what's actually happening in this contamination, how does it consist, and probably in the end also have an even better way to prevent this contamination from happening. So to sum it up, as I've spent a lot of time now, PPA offers best performance that we know of, and we're actually improved a lot over the last years. There is a possibility to functionalize it with these silane side chains or the copolymers, or adding photoacid generators to improve some performance in this single field even more, and that a lot of improvements are ongoing. The resist testing is one of the continuous projects in our application lab. You can also use a variety of other resists, quite easy to try in the NanoFrazor. Give us a sample, put it in the NanoFrazor, see if you can pattern. It's quite fast done. Then we can measure the tip status and the contamination in the tool itself. You don't need an SCM for that, and you get a direct feedback how well your patterning was. And the tip endurance is also quite good now. We can write actually for multiple days straight. So I actually started some experiments on a Friday, and it was still running on Monday when I came back. So this is also quite nice. So that sums it up there. And I hope I could answer all the questions for the questionnaire that you now have a couple of minutes to finish. And I give the word back to Niels. Thank you all.